Okay, hello and welcome to my experiment 2 for my microprocessors 108L. I'm Carl Castillo from from section E01 of CPE108L, and today we're going to do the second experiment. Let's okay, so the very first instruction here is to launch the EdSim simulator, so I already launched it here. And a time delay is used to set the number of times that the part of the program should be executed. So we click new and encode the following instructions at the IDE. So this is case sensitive. So we have org. Again, this is used for initialization of the address using the hexadecimal. So main and colon clear A. That is to clear the accumulator. We have move A with hexadecimal 6 and move B is for hexadecimal 3. And here we have our new function called again with decrement A. So we will be subtracting 1 from the what do you call this, the register accumulator. So let's just put it here, and DJ and C B comma again. So it is explained here that subtracting 1 from the content register B, this is register B, it will be decremented until it reaches 0. So if it is not 0, then it will do this function again and the program. So let's see. So for this program, we choose 1 for its speed. So let's save this one with experiment 2 part 1. Okay, let's click assemble, and it says no errors here. Observe the output and click run. So yeah, it happened pretty fast, but our accumulator started from 3. For our B started at 3, and then with the again function, it slowly decremented until it reaches 0. And if we look at our accumulator with deck A, so our accumulator A contains 6 hexadecimal, but since our condition here uh, is based on the B, register B, so once our B is 0, it will stop the loop, the loop for again. So that's why our accumulator contains 3, and the program actually stops. So click pause to stop the program execution. Click reset. Let's click reset and click assemble. So let's look at let's click step and observe. So here our accumulator will now have a value of 6. So as you can see, 6. If we step again, our register B contains 3, and since we have the again function, it will go on again. We will do the decrement A. So our accumulator changed from 6 to 5, and our conditional decrementor here, DJNC, means decrement jump if not 0. So once, so let's step again. So since our B is not 0, after we decrement it, B is not 0, so we go on the again loop. So let's step again. Our A is now 4, so from 5 to 4, and if we run this, if we step again, our B is now 1, and the again loop was triggered, and our accumulator is now 3, and if we run it again, we decrement b, and since after decrementing b it is 0, it reaches the end part of the program. So click pause. So let's see. Uh, Click reset. So we reset and change 6 to, let's change 6 to F. Let's see. How many F? 4. 4 Fs into. So let's click assemble. Oh, so we remove the number sign, I believe. Okay, so let's click assemble and answer question 1. So question 1 is, was there an error? Yes, there is an error. So I will fix the format later. But yes, because the second argument for move instruction was not an actual number because of the lack of number sign. So if we add number sign, let's see, so it will still be wrong. FFF. So I believe, uh, because first of all there's no number sign, so uh, this part is considered uh, as an address. But since there are no FFF, FH, and FFH, so it will not work. So let's try commenting this one. And as you can see, there's also an error on move and we. But let's see if we add this one, there's still an error. So uh, hold on. Okay, so here uh, there's an error because, so again, it was not an actual number because of the lack of number sign. But as you can see, if we add 0 here and assemble, it will produce no error. So uh, the I think what happens here is that the processor uh, cannot distinguish the if the argument f f f f h is a variable or an actual number. So if we add a number sign, if we try to assemble it, it will not work because of the limit of the hexadecimal and of our memory. But if we try running here, so let's try. Let's see what will happen. So again, this one uh, already exceeded the value. So or wait. So continuing to my question one right here. Okay, so I think I figured it out. Is when we try using when we are using numbers, when we are using letters to uh, when we are using letters as number, for example in the hexadecimal the value of f is 15. So when we are using letters, the processor cannot distinguish it from whether it is a variable or a number. So with that, we need to explicitly state that it is a number by adding a 0 on the start. So if we try and run this one, so as you can see, our v is now fb. So we actually start the value ff. So let's try to reset here and add. So regardless of the number sign. So uh, if we are dealing with letters, so let's say for example, our most significant bit that we are trying to store is a letter. So we must append a numbers A0 from the steps to indicate that this combination of letters are actually numeric values that we want to use. So let's try to assemble. So as you can see, we actually stored the value for the F7. So we F3, it is decrementing. And so yes, because the second was not, so let me just rephrase it. Was not clear whether if it is a variable or an actual numeric value to implicitly say to explicitly say that it is a numeric value. A0 is appended before the letters. So in this case, we are using F, uh, which in this case a hexadecimal FF will be 0FF in order to be recognized as a numeric value. So that's for the first one. So let's go to our okay. Pause, save the encoded program and add the so okay, so let's see. So let's remove. So this one. So let's save experiment 2 part 1. So let's override experiment 2 part 1. Okay. Let me check if I'm recording. Okay, I'm recording. Save the info. Add the following into the excuse me. Using R0 as a counter and store it with 03H. Add the contents of okay. So you just do let's do the step 16. So, okay. Okay. Let's use A. Okay. So we will be using R0. So let's just comment this one out. So since we are using R0 as counter, we type DJ and Z R0 again. And we have our move R0 with number sign 03H. Okay. So use register R0 as a counter and store it with. So since B is our counter, we will be removing that and add the contents of register. So I think since you are still using B, I mean yeah, let's continue. Decrement A, so here we'll be adding the add A, B. So since A is the first one, add A, and our resultant will be stored in A. And display the result count. Move B1 A. So let's try assembling this. Oh, so there's an error. So let's see. Let's use this one. So let's use the very first value. So the number 06 and this one number 03. Let's assemble and so that is 6. What one? Pause. Let me pause. Let's reset. Our R0 contains 2. So let me just reset everything. So everything is 0. Let's assemble and run. Our here we have 3. Now we have 2. Oh, so I think we need to change DJ and Z B again. So because if we go on this line, this whole thing. No. Let's try running it first. So our accumulator. Wait. Uh, yes. So let's try changing this to FB. Okay. So three. So let's see. So let me just what? Let's reset and let's try adding them before decrementing. So let's run. And our program ended. So okay, let me just check something. Okay, so going back to my step 2 here. So let me just recode this one. So add the following into the encoded program. So I think we will be keeping the old program. So a, a, yeah. Okay. So we will have the count function. So here var 0 h will be 1A and display the results. So let's try running this. So assemble and run. So it will take a very long time. So let's increase. Okay, that is too fast. Oh, wait, let me check my recording. Okay, I'm recording. Okay, so that was too fast. So pause, please, and just assemble, and let's reset everything to 0, and then let's run. So here, okay, so still that was too fast. Okay, we'll be using uh, frequency 1 just to slow it down, and we just need to wait. So let's just look at our R0. So since we'll be using that as a counter, so it will take a long time since our B started at FF, hexadecimal FF, and we are slowly decrementing it using the again function. So it will decrement A and B at the same time. And since our B is still not 0, it will forever, it will continue looping here and again. So okay, we are close. We are now at 888. So let's wait. Let's wait. Okay, we are now at 4B, hexadecimal 4B. Okay, we are now close. Okay, now we are at 2B. Okay, we are really close. So okay, we are now at single digit hexa. Okay, let's look at our R0 right here. 2. Okay, so I think I made an error. So we are this one should be count. So let's try running it. So that after running the decrement jump, if not 0, for R0 it will go straight back to our count. So we play the waiting game until our B is 0. So notice that I corrected the error with the addition of 0 before the FFF FFFF hexadecimal value. Okay, so we have A4. So okay. So here I forgot to explain here the display to the step D 16D display the result in port 1. So here excuse me, so P1 is a port for our LEDs, for our 7-segment display right here, one of the 7-segment display. We just move the value from the A, so the sum is in register A, so we just move A to our P1. So we are now at 2B. We are now at 1 single digit hexa, so let's look at our R0. Okay, we are now at reaching R0, so 0. So there, as you can see, uh, our accumulator did not add anything, so I think that's because of the values right here. It already exceeded our values, so that's why we don't get anything. So let's try using the old values. So let's try 06H and 03H. So okay, so try assemble and let's run it. So in that way, you will have a value. So let's reset. Uh, I forgot to reset everything. So let's sample. Let's run it. Let's look at our accumulator. As you can see, 0 plus 3. If we look at here, 0 plus 3 is still 3, so our accumulator did not change. But if we go back to our, uh, this might take a while again. Uh, let's see what will happen. So let's speed it up to 100. So if we look at it, if we add our value a, so since we are decrementing sa power, so let's try set sample. If we pause, we can set. Okay, so that's good. Okay, I'm recording. Still recording. Okay. Can we increase this by 10? Okay, we can do that. So it's a bit faster. Okay, so let's slow it down. Okay, skip. So wait, let me check something. So after further testing, I realized that there's a plus button here that can enlarge the screen. So that's very helpful. So since I'm doing the step 16 of the part 1, I've been having a trouble in getting this one because uh, we are I'm instructed to change the 06 into FFFH and 03 to FFH, so that contains an error. So I fixed that by appending a number 0 on the uh, leftmost side of the numbers, so 0FFFH and 0FFH, and that will work. But since the maximum value that this can store is just FF, they are actually the same. So the FFFFH or A will turn into FFH, and B is contains FFH, so they will be basically the same. So in the end, when we run it, so as you can see, so let's try it. So let's try FFH and FFH, and if we run this one and increase the speed, so as you can see, it will all turn to 0. So since we are both decrementing a and b at the same time with the again function, and we're just adding this new program. So let's use register 0 as a counter and store it with 03h. So I did that with uh, adding the move r0 with number sign 03h on the main, so that our r0 will contain a 3 hexadecimal, and we add the contents of register. Uh, we use R0 as a counter, so this is the part DJNZ R0 comma count. So it will be a counter of itself, and we add the contents of register A and B, and we store the sum in A. So that's already given. Display the port on P1, so move P1 comma A. That, and then we answer. So as you can see, we will have a value of 0 if we use the these values right here. But if we reset, we use the very first, so let me just run this one, and let me take a screenshot of this, so that so so let me just pause the program. So this is for the question 3. So okay, let's go back. So let's reset. But if we are going to use the very first values that we have, 0603, and we run this one, and actually use the update frequency of 1, reset, and run. So as you can see, uh, that happened too fast. So let's see. Here R0 is actually a counter. So after R0 is now 0, we add A and B, but the value of B is actually decremented until 0 with the again function, since I'm instructed to add this additional part. So in the end, we will still have the same value for the accumulator, which is 3. So the output pins is actually like this. So let me just take a screenshot and save it there. But if we will remove this one, uh, we will remove this one. So let's comment this one. Sorry, comment this one. So this green part is commented. So as a symbol. So we will have a different value. So wait, that happened way too quick. So assemble and let's step. So okay, first we initialize the values. Decrementor at 6, RB with 3, and our R0 with 3. So with the DJ and Z R0, so we step. So as you can see, we already decremented twice. So for the final, uh, step, and then we add A and B. We now have 6 plus 3 is 9. So our accumulated value is 9. And then we move the what do you call this? And then we move the value from our accumulator, which is 09, to our LED one. So here, so this is 011. I don't actually know the value. So 011, 0111. I think that's how it works. But this is the output if we comment the again function. So let me just take a screenshot of this. So okay, let me just delete. So delete. Uh, it's nice. So I just minimize everything. So I can just remove the wrong ones later. So I'll be checking this one, this part again later after recording this video. So that's for our question 3. So for our question 2, the new added code right here is this part. So just gonna copy this, and this will be our what happened. Okay, there's an answer there. That's a new code. So our new code is this one. I'll be double checking to make the output faster. What line of the new program should be changed? Okay, so for the question 4, let me just okay. So continuing to my question. So here on the question 4, to make the output faster, the line, the answer here is the time delay function or the counter. So to make the output faster, the counter right here must be smaller. So if we reduce this to 2 or to 1, then our output will be faster. So as you can see there, we have an output, but if we turn it into 1, there. So at 23 micro, so let's say 20 microseconds, we have an output. But if we revert it to 3, okay, so that is very small. So let's try a bigger number. Let's say 7. So if we use 7, the output is around 30. So if we use 3 again, if this is uh, so if we use 7, we have an output at 30, and if we use 3, we have an output around 22 microseconds. So definitely, if we the time delay function or the counter must be smaller in order to increase the speed of output. And here, for the question 5, what is instruction to be added in order to display the output? So, since here, the binary of 3 is 1, 1, or in this case, since we are dealing with 7 segment display, so this is 1, 2, 3, 4, 5, 6, 7 digit binary. So, the output of must be the binary of 3 will be 1, 2, 3, 4, 5. So 5 zeros and then 1, 1. So which means we need to complement this one. So the complement and the command for complement is CPL-A. So we complement the A before moving it into P1. So let's assemble, let's run, and there we go. So we have our binary of what do you call this? The proper binary of our accumulator 1, 1. So you can see the value of actual accumulator is also complemented, which is FC. But in our display, the output is right. So as you can see, we have, so this is G F. This is the most significant. So G F A B C D E F G. So G F E D C B A. So we have 0 0 0 0 0 1 1, which is the proper binary of 3. So that is for uh, CPL 8. I will change that later. So we are now reaching part 2. So I think what I'll be using on my on the question 16 with regards to the question 3 is this one. So since by following the procedures, the only thing that I will change is this one. So instead of using FFH for my step 16, I will be using number sign 06 and number sign 03. So I think there's no hexadecimal right here. So let's see. All right. So no, there will be a hexadecimal. So I already did that. So that's the only thing that I would change, but everything else will stay the same. So we still have the again function from our step 2 part 1, and we will just be adding the count function right here. So following the steps, so first we register our 0 and use it as a counter, and this is that part. And then after doing that, we add the contents of register and we complement it, and then we move the value of our accumulator to our pins one, or let the 7 segment display. So okay, so let's save this one. Okay, yes, overwrite it. Yes. Okay, so for the next step, click new, create a new file. Okay, so again, we start at the address quadruple 0h, and we have the main colon here A. Make sure that our accumulator is 0. Get in. So we have our function get in. We have called delay move excuse me, move A, P2, excuse me, we complement A, JZ, DC get in, CPLA, move P1, let's move P1 to A. Okay, so the thing that I noticed that every time we are dealing with the 7-second displays on the bottom, we need to complement them first. Okay, so move B1A and we call rot. So after calling rot, we now define the function for rot, which is let me just combine them together, which is RLA, which means rotate left the content of the register combinator. So I think that means shift left delete. So yes, move P1, comma A, call rot. We call rot again, so we will continuously call that. So now we add our delay function. So we have move R0, move R0 number sign 0FH. So as you can see, instead of using just number sign FH, we use number sign 0FH to indicate that it is a digit. So after that, we will be using L1. So I think this defines that L1 means move R1 with 01H. So let's see, 01H. And our L2 means move R2, number sign 01H. Oh, they are both 01H. Okay, 01H. And I think let me just copy paste this. Hey, you know what? So it means decrement R2 until it gets 0. So with the dollar sign, so it is a delay. So since okay, you know what? Let's just code everything first before DJ and Z R0 L1 and return, and then we end our program. So after press two switches, so I don't know which one is actually our switch, so we'll be testing it. So let's see, we are instructed to assemble it, we have no errors, we run, is it running? We run, okay, 6 5 4 3 2 1 0. Okay, let's see, observe the output. So I don't know how to press the switch. So is this, am I pressing the switch properly? So I think since state A move B1, since our pins, our LED here is not, what do you call this, is not outputting properly, so we aren't actually pressing anything. So ADC, then touch it. Uh-oh, okay, I think so why is Okay. Okay. Okay, let me check something first. Oh wait. Okay, so going back to our program. So let's reset it. Oh, let's store the value right here. Okay. Okay. So let's see. Let's so let's try resetting everything. Let's just access them manually. So we have okay. Oh, no, no, no. Should be good. Okay, so we must be at 4 to 4. This is oh let me just pause this one. Okay, you know what? Let's just continue. Let's reset and let's try running it on. Okay, symbol. Let's run. Okay, so going to our instructions right here. Let me check if my mic is on. Mic is on. Everything is on. So press two switches at the same time. Okay, so we just press this one at the same time. So these are the switches that we need to press. So we just wait for the delay to finish. Okay, so here now we have our output right here. So it's like a snake's thingy. So it's like a snake, like the snake game on the Nokia 3310. So let's answer question one. Uh, what is the final output? So the the okay, wait. Oh, okay. So okay, so this one is actually 0011. The output of the program is the shifted is the left shift value of how many we have 8 bits right here, so 0000 and ones. So this means that the the highest bit will be the lowest bit on the next run. For example, after the initial value 234, the next value on our LED 7 segment is you know, display will be 000010. So as you can see, this bit right here was moved on the least significant bit. Most pala, most significant bit will be the least significant bit. Okay. Okay. So we answered that. So wow, our register has a lot of 12 values. So okay, pause ko now. Click reset. And click reset. Change RL to RR. So what I'm expecting here is a shift right movement. So change the press switch. So oh yeah, so I forgot to indicate that earlier I was using this one right here. I pressed 0 and 1, so the bits of the 8 bits, the 8-bit value of this one is actually shifted. So see, so it will go like this, so they go like this, like this, like this. So let's try different patterns. So instead of this pattern, let's try this pattern for instance. So since we are now using RR, so let's assemble, no errors, and we run. Okay, since we are pressing this one, I'm expecting it to go. So first there's a delay. Okay, after completing the delay, okay, so as you can see, the colors right here is now shifting to the right. So let's try answering the question 3 and 4. So is it the question 3? I mean the question. It's question 2. So okay. Okay, so let's see. Okay, so this one is how is it B7? Oh, I get that this one is D. So this E. If we check for button of E, E checks out this. So let's search for that. E. Oh, okay. So okay. I think I get it. So this one is E because this one is 1110, and this one is B because this is 1011. Okay. So okay. Illustrate how instruction executed C contents of accumulator register relative data. Okay, so the accumulator register contains the actual hexadecimal numeric value. But since we are dealing with the 7 segment display, we need and it uses the complement of the stored values as its bind 8-bit binary value to turn on the right LEDs. We need to take the complement of our original value. So let's say for example, here we have EP stored in our accumulator. And if we call this, if we take the binary of E, so the binary value of E is right here, which is 1110. So let's just open this one for faster. Okay, so if we look at our binary of B, which is 1011, and for our E is 3110, and if we look at our value rate, no, sorry, okay, let's do that for this one. So here the complement of it is, the complement of our B is actually 0001. So of our E is 0001, so as you can see, it's just the complement of it. So, and with regards, so if we set this one E, and we have E F, and our B becomes 7. So this 0000 binary of 7. Okay. Okay. So here, okay, we have BE again. Okay, so I think that explains it. The accumulator register contains the actual hexadecimal numeric value. And since we're dealing with the 7-second display and it uses the complement of the stored values as its 8-bit binary value to turn on the right LEDs of the 7-second display, we need to take the complement of our original values. So the the RL performs the shift left on our on the values, while the RR performs the shift right, and depending on the uh, input right here. So since this is my two buttons that I press, it will shift to the right at a certain what do you call this, certain interval. So it purely depends on this. So say for example we input this one, then the shift of it will differ from the interval of shifting will vary from this one and this one. It will be different. So let's see. Change the value of R0 to a lower hexadecimal value on the program. What is the effect of changing the value of R0 to odd in the program? So let's see. Let's do that. So let me check if I'm recording. Yes, I am recording. Okay, so let's reset. Let's change our R0 to smaller value. So let's say let's do 8. Okay, so assemble. Let's run. Okay. Oh, I'm not pressing anything. I forgot. So, okay, let's wait for the delay to be finished. Okay, so as you can see, so since we lower the delay, the initial value for our delay, uh, the program accepts input much faster. So okay, let's reset it. So okay, so let's turn it back to F, and we already pre-pressed the values, so let's assemble and run. Okay, okay, 3, 2, 1, 0, and then it accepts. So at around 90 instructions, it accepted the input right here. So if we lower it, let's say very small, let's try 3. So that is very small. So let's run it. No, no, no. Okay, let's pre-press everything else. So 2, 1, we run it with R03. The program uh, runs, accepts. The delay becomes shorter. So the delay becomes shorter. Instead of counting down from 15, which is the value of RF, hexadecimal, uh, the program counted at 3, which is number sign 03H. So the delay becomes shorter, thus the program accepts an input in a much shorter time delay interval. So what is the importance of the instruction ret in assembly language? So I believe right here, so since we are okay, so here if let's try running it without the return function. Okay, symbol, let's run. If we remove the return function, our program stops because after going to our function delay, the next step after delay is end, and that will end our program. So as you can see, no operation was performed on our registers. So if we add the return, if we include the return again, it will return to the line where the delay was called. So after going right here, decrementing R0, so you see 01. After our R0 returns becomes 0, it returns to this function and it moves A to P2 and complements the A since uh, our A contains 0. So we, what do you call this? Our A contains 000, contains nothing. So since our A doesn't have anything, it's just store nothing right here. So after it moves it to P2, wait, okay. Our A contains 0, and if we get the complement 0, uh, since nothing is stored in A, so nothing is displayed on our wait, I'm reading so we move the value of our P2 right here to A. So since our P2 right here doesn't contain anything, yeah, the value there is just stored in our accumulator. So let's see. Alright, okay. Okay, so as you can see, there's a brief moment that our accumulator becomes FF. So we complement the, after we get the value FF, we complement the value FF, and now we have the value 00. And with that jump get in, so it means if there are no buttons that were pressed, we jump on the get in again. So we go back to our get in and then we call our delay. And since delay have a return, after running this part, we will return to our program instructions 1 and then continues on accordingly. So until we have a button pressed, that's the time where we will do the rest of the code right here, which is CPLA until our rotate. Alright, so let me just type that. The return acts as a what do you call this? time determinable. The the ret is a return function that goes back to the program counter where the function is called. In this case, delay was our function, and after finishing the delay, a ret was called in order to perform the and has a PC at 001 for the PC 003 and so on. If return is not present after running the PC, the PC 001C 001C, the next line is end, so the program will terminate. Okay, so I think I answered that part already. Okay. Flowchart below illustrates, so that is for my question 3 and 4. The flowchart below illustrates the normal flow of an output with time delay of another. Okay, so start initially setting of the ports. Read from input port. So if we look at our flow right here, it says start, initialize the variables, set up the ports, read from input, operation process, write to output, port, time delay. So if we look at here, so actually it is inverse. So the time delay must be first. So here, so we initialize, this is the initialize. We call the delay. Okay, wait. We call the delay. We call the delay first. So setting up the ports. What is? Let me just search. What is setting? So since here move A we take the value of P2, which is 0, but the complement of it is FF. So okay, so I think the right uh, the right value the right flowchart right here is start initialization, and then we set up the ports, and then after setting up the ports we have a time delay right there, because as you can see, if we run this part, if we run this one, as you can see, we already pressing the buttons, but the program is not taking any inputs until the delay was over. So after delay is over, we read the input from the port. We read the input from the port, and then we do the operation process, which is the rotate. We write to output the port, that is the move P1A. We call rot, but we call rot, so the rotate. So after this, there's a loop right here that goes back to our operation process. But if the input is not present, there are no input, the time that after writing out to the port, the time delay will go, we will go back to our time delay. Okay, so I think that answers, I will convert it later uh, to the flowchart, but I think that concludes my video demonstration. So let's go back to our conclusion part. So, so in this video, I apply what I learned in experiment 1. Understand the use of instruction set of 8051. So the newly added instruction, besides the move, add, clear, uh, move, add, clear, we have the new additions of functions such as get in, and we have the function call, which calls the function that we created, and we have here the P1, which is our 7 segment display right here. So this is P1, P2, P3, P4, and we have here our dollar sign. So this means that the program will stay on program counter 18 until it reaches 0. So let me check again if I got it right. So the dollar sign, decrement R2. Alright, so the dollar sign means decrement R2 until it becomes 0. Otherwise, will remain in this line. So that is the purpose of dollar sign, is to remain on that line. Okay. Uh, I also learned about the RR, that is the shift right, and the RL, which is the shift left. So JZ is actually new, which is jump. Let's see, what is JZ? So jump if no switch is pressed, that is JZ. And DJ and Z, jump if uh, jump to again. Wait. Subtract 1 from the content of the register B until it becomes 0. So if it becomes 0, it will jump 2 again. So that is the purpose of BJNC. So uh, that is mainly used as a counter. So as you can see here, B is our counter. In this case, we change it to R0 on our part 1. Okay, let me just check. I also learned that in order for our delay to be lesser, or to take less time, we must use the smaller value for our initialized variable for our counter. So in this case, right here on the question 3, if we change our R0 right here, so this is our counter variable right here, because mainly on our R2 and R1, that is initialized as with a value of hexadecimal 1. So that is the lowest it can be for our R2 and R1. And for R0, since we are starting at F value, uh, it will take 15 more times before completing the delay. But if we reduce it to 3, then it will take 3 more iterations, which is clearly much faster than 15. And then we will go back to our other programs right here. So we also learned that CPL is a command for complement, and the ports right here, the P1, P2, and so on, uses the complement of our actual value. So as you can see right here, we have 9Fs. So if we complement this, we will have 1001, which is the binary of 9, and we complement 0000. The complement of that is F, so that is actually 1111. So since the ports uses the complement of our stored value as our 8-bit binary value to turn on the proper lights, we will take the complement of our actual value and then use that complemented value to turn on the right LEDs on our 7-segment displays right here. So okay, so I think I covered that one. So the use of instruction set in creating a time delay. So uh, these functions right here can be considered as a new instruction set, since we are calling, we are jumping and calling to that part of the program. So demonstrate how the I/O interface work during time delay. So as you can see, if we, as I explained earlier, and if we run this one, there's a jump right here. Uh, the part of here is jumping, as you can see. No, I mean, not that one, because that's actually the shift register, but the jump right here, the GZ. And understand the use of flowcharts in programming. So as you can see right here, this is flow. So our question part 2, number 2, number 2. Okay, so number 2. So as you can see, we have a delay first before reading the output, reading the input, and then we perform the process. After performing the process, we output it on the pins right here. I don't know why it stopped, but I think my program is just bugging. So right, so and as you can see right here on the function rotate, we are calling rotate again. So this is an infinite loop. So after calling rotate right here, we go to rotate, we take the shift right of our accumulator A, we move A to our P1. So this one right here, and then we call route again. So as you can see, we are stuck in this loop. So error, function set as not called, because there are some parts of the program that will never be called again because we are stuck in this loop. So the proper here is that after setting up the ports, we have the time delay, we read the input, we perform the process, we route the output to our port, and then we loop again to our operation process. And there's actually like no end right here. So there. So that concludes my assignment 2. So my name is Castillo from CPE108L, section E01, and thank you for watching.